What if I told you there's a speed you can never beat? Not a car, not a rocket, not even your wildest imagination. The universe has a limit, and it's light. I'm Richard Feynman, Nobel Prize-winning physicist, quantum mechanic, and eternal troublemaker. And today we're going to chase that cosmic wall together. Think about this. You're on a rocket. You've broken every record in history. You're going faster than anything humans have ever built. And then you hit the wall. A wall made not of steel, not of force, but of pure light itself. Suddenly, physics becomes a cage. And curiosity? Well, curiosity becomes your only way out. I've spent my life asking questions most people thought were crazy. How does a particle know where to go? How can light act like a wave and a particle at the same time? Why can't anything ever go faster than light? These questions aren't just abstract. They're the keys to understanding the universe. In this video, you'll discover why the speed of light is the ultimate limit, not just a number in a textbook. You'll see how my work in quantum electrodynamics reshaped how we see particles in light, and how tiny diagrams I drew on a scrap of paper predict the behavior of the entire universe. And yes, by the end, you might start seeing the universe in ways you never thought possible. Along the way, I'll share stories you won't find in the history books, like the time I solved a problem nobody could touch using a piece of chalk and a napkin, or how curiosity led me to breakthroughs that changed physics forever. This isn't just science, it's a journey into the deepest mysteries of reality itself. Welcome to Feynman Flux, where curiosity meets the cosmos. If you love physics, mysteries, and the thrill of discovery, subscribe now and join me as we push the boundaries of what we know. What if I told you there's a wall in the universe that no one, not rockets, not particles, not even your imagination can ever break? A wall that's invisible, untouchable, yet absolute. That wall is light, and I spent much of my life trying to explain not just the wall itself, but the strange, almost magical rules that make it unbreakable. I'm Richard Feynman, Nobel Prize-winning physicist, quantum explorer, and professional curiosity enthusiast, and today you're going to see why the universe's speed limit is far stranger than anything you've imagined. I suppose it all started when I was a kid in Far Rockaway, New York. I wasn't the kind of child who played quietly with blocks. No, I took things apart. Radios, clocks, you name it. I wanted to know how they worked. I once dismantled our family's radio, piece by piece, just to see how the sound traveled through wires and vacuum tubes. Most kids would have seen it as broken. I saw it as a puzzle. That same curiosity would follow me into a lifetime of studying the quantum world, a world where puzzles are the rules of reality, not the exceptions. By the time I was grown, I'd won the Nobel Prize for my work in quantum electrodynamics, or QED, which is a fancy way of saying I figured out how light and matter dance together in ways that seem impossible. And yet, I never lost the sense of play that got me there. I approached physics like a kid with a new toy, except the toy was the universe itself, and the cosmic wall, light speed, that was the ultimate challenge. So what is this wall? Why can't anything surpass it? Imagine a race you can never win. You could pedal a bicycle as fast as your legs allow, rocket across the desert at hundreds of miles per hour, even blast off in a spaceship close to the speed of light. But there's always something just ahead, always a limit you cannot touch. That's light. Photons, the tiny packets of energy that carry light, move at the fastest speed possible in the universe, 299,792 kilometers per second. Faster than anything we've built, faster than anything we can imagine. And yet, even these photons, these blazing travelers, follow rules that are stranger than any speedometer can measure. Now you might think, well, light is just light. It's a beam that moves. But light isn't simple. It's both a particle and a wave. It behaves in ways that defy common sense, bouncing, splitting, and interfering with itself in ways that made even the smartest physicists scratch their heads. And that's where my approach comes in. Instead of trying to force nature into neat little boxes, I asked a different kind of question. What if a particle doesn't just take one path, but every possible path at once? That was the idea behind what I call the path integral formulation of quantum mechanics. It's a mouthful, yes, but the essence is simple. The universe is full of possibilities, and light explores all of them simultaneously, always choosing in ways we can predict only probabilistically. To see it another way, imagine you're trying to walk across a room. Normally, you'd pick a path, maybe the shortest one. But in the quantum world, a particle doesn't just pick one path. It tries every single path it could take. Straight lines, zigzags, even loops around the furniture. And somehow, when you add up all the possibilities, a pattern emerges. That's the hidden order behind the apparent chaos of light and particles. And that's how I began to understand the cosmic wall, not as an arbitrary limit, but as a natural consequence of the rules that govern every photon, every electron, every flicker of energy in the universe. I should also tell you, I wasn't always serious about physics. In fact, some of my best insights came when I was goofing off. When I worked on the Manhattan Project, building the atomic bomb, I learned not just the physics, but the importance of curiosity, of asking questions that others ignored. I played drums, picked locks, taught myself to draw, and even once cracked a safe in Los Alamos just for the challenge. And through all of this, the lesson was the same. Curiosity is more powerful than fear, more powerful than authority, and often more powerful than formal education.
Curiosity guided me to the heart of quantum mechanics. And it can guide you too. You see, the cosmic wall isn't just a rule. It's an invitation. It's an invitation to wonder, to experiment, to imagine what the universe looks like when you bend the rules in your mind. When I explain photons taking every path at once, when I show how light bends around corners and through slits in ways that seem impossible, I'm not just teaching physics. I'm showing the power of asking why, and then following the answer wherever it leads, even if it seems absurd.
Here's something few people know about me. When I was very young, I once convinced my mother to let me build a tiny model of a nuclear chain reaction in our kitchen using a few scraps of metal and cardboard. Of course, it wasn't a real chain reaction, but the experiment taught me more about cause and effect, about energy, and about the joy of seeing an idea come alive than any book ever could. And that same joy, that same unrelenting curiosity is what drove me to understand why nothing can beat light. Now imagine this, you're racing, trying to catch a beam of light, you push harder, pedal faster, calculate every angle, and still light is always ahead. But here's the counterintuitive twist in the quantum world, that always ahead isn't just speed, it's probability, it's interference, it's every possible route a photon can take, interacting with every other possibility. And by studying these interactions, by mapping them with little diagrams and equations, you can actually predict patterns in the chaos. You can understand, in some sense, the very skeleton of reality itself. And that's the core of my philosophy. Embrace curiosity. Don't settle for what's comfortable. Don't accept the limits you see at first glance. Ask questions, break things apart, put them together. Play with ideas the way a child plays with building blocks, because sometimes the universe only reveals its secrets to the playful, the inquisitive, the unafraid. That's how I approach the cosmic wall. Not as a barrier, but as a puzzle. And every puzzle in physics, no matter how impossible it seems, can be understood if you chase it with curiosity, rigor, and a little bit of mischief. So I ask you now, while the photons race overhead and the universe unfolds around you, what question would you ask the universe if you could? What puzzle would you chase if there were no limits? Because that's the kind of thinking that led me to understand light, particles, and the invisible walls that define reality. And it's the kind of thinking that can lead any one scientist or dreamer to discoveries that change everything. I'm Richard Feynman. And in this video, we're not just talking about physics. We're talking about curiosity, about exploring the impossible, about understanding the rules that make the universe both maddening and beautiful. Stay with me, because the cosmic wall is only the beginning. The real journey begins when you see that the wall is also a window, and that everything you thought you knew about light, speed, and reality can be seen in a completely new way.
Light speed. Just saying it feels fast, doesn't it? Faster than anything we experience. Faster than a jet. Faster than a rocket. Faster than the fastest thing you can imagine. But here's the kicker. Even at that speed, the universe still stretches beyond comprehension. And there's a reason I spent years staring at equations, doodling diagrams, and asking questions that sounded completely insane to most people. I'm Richard Feynman, Nobel Prize-winning physicist, quantum troublemaker, and lifelong student of the curious. And today you're going to see why light speed isn't just fast, it's mind-blowing.
Let's start with something you can picture. The Earth to the Sun, about 93 million miles. At light speed, that distance would take roughly 8 minutes to cross. Sounds quick, right? But the nearest star, Proxima Centauri, is more than 4 light years away. 4 light years. That means even if you were moving at the ultimate cosmic limit, it would take more than 4 years to get there. And that's just the closest star. The galaxy, billions of stars. The universe, unimaginably vast. Even light, the fastest traveler in existence, can't escape how enormous the cosmos really is. The speed of light isn't just a number. It's a cosmic ruler, a boundary line for everything we can ever hope to reach. Now you might ask, why can't anything go faster than light? That's exactly the kind of question that got me into trouble and into discoveries that would earn a Nobel Prize in physics. My work in quantum electrodynamics, or QED, was all about understanding the strange dance between light and matter. Particles don't behave like billiard balls. Photons don't just zip in straight lines. They take every possible path at once. They interact, they interfere, they create predictable patterns, yes, but only when you look at all the possibilities together. And this is where Feynman diagrams come in. My little sketches that show how particles bounce, split, and merge. These diagrams aren't just doodles. They're tools for predicting the behavior of the universe itself. People often think quantum mechanics is too complicated for ordinary humans. But that's wrong. The principles are strange, yes, but they're also simple when you see them the right way. Think of a particle moving from point A to point B. In classical physics, it picks one path and sticks to it. In my world, it doesn't. It tries every path, exploring every possibility simultaneously. And somehow, when you add up all the possibilities, you get the patterns we observe. This is the heart of quantum mechanics, the engine behind QED, and the reason light speed behaves the way it does. Particles don't just obey rules. They explore them, play with them, and in doing so reveal the hidden architecture of the cosmos. When I first started drawing these diagrams, people thought I was being playful, maybe even reckless. And I was. That's how I approached all physics: curiosity first, formality second. I was never content with memorizing formulas or reciting theories. I wanted to see, to touch, to play with the ideas. That curiosity took me from doodling on napkins to contributing to the Manhattan Project, building the atomic bomb, and then on to the deeper mysteries of the quantum world. Even in those high-stakes environments, I kept asking questions that seemed trivial. What if we look at this from another angle? What if the particle could do something else? And time and again, those questions led to insights no one else expected. Let's go back to light for a moment. You might think of it as a beam. Straightforward, simple. But in reality, light is a quantum circus. Photons can take multiple paths, interfere with themselves, and even cancel each other out in strange ways. My diagrams help us see this not just in theory, but in a way that makes predictions accurate to incredible precision. It's a little like having a map of the invisible. You can't see the roads directly, but with the map you can predict exactly where traffic will flow. And that's exactly what I did for the universe's tiniest travelers. This isn't just theory for theory's sake. Understanding light and particle interactions underpins modern physics application. Nanotechnology, quantum computing, even the GPS in your pocket, all rely on principles I explored with pen and paper decades ago. And yet it all comes back to one simple, impossible truth. Nothing can go faster than light. That speed limit isn't just arbitrary. It's baked into the very fabric of space and time. Try to exceed it, and reality itself resists. Time slows, distances stretch, and energy requirements become infinite. That's why light is the cosmic wall, and why everything else must play by its rules. Here's a little story you might not know. When I was younger, I would spend hours drawing imaginary circuits, imagining how particles move and interact. Sometimes I'd even create little games, predicting where an electron would go next, then testing my ideas with experiments. Most of the time I was wrong, but the mistakes mattered more than the successes. Each failure revealed patterns, quirks, and exceptions that hinted at deeper truths. And that playful habit of questioning, exploring, and experimenting never left me. That's why my approach to light speed and quantum mechanics is as much about curiosity as it is about equations. The more you study light, the stranger it gets. Imagine photons racing across the cosmos, taking every path, interfering with themselves, shaping the universe in ways that seem almost magical. Imagine electrons splitting, recombining, popping into existence and vanishing again, all governed by probabilities, not certainties. And yet somehow when you put all these interactions together, a pattern emerges, a structure, a law. And that's what light speed is, a law, a limit, a cosmic truth that ties together the smallest particle in the largest galaxy. Could we ever break the cosmic wall? Could we ever go faster than light? Probably not. But that question itself sparks the curiosity that drives science forward. By exploring the limits, by testing the boundaries, by asking the impossible, we discover not just what the universe allows, but what it values, what it hides, and what it reveals when we look closely. That's the lesson from QED, from Feynman diagrams, from the Manhattan Project, and from every tiny experiment I ever ran. Curiosity is the only engine powerful enough to push us to the edge of understanding and beyond. And that's why light speed will always blow your mind. Not because it's fast, not because it's unreachable, but because it's a window into a universe that operates by rules far stranger than common sense. Rules that particles explore with reckless abandon, and rules that we, with a little curiosity and a lot of play, can begin to understand. So when you think about light, don't just imagine a beam or a flash. Imagine a race you can never win, a map of probabilities, a circus of particles, and a cosmic wall that defines the edge of reality. And then imagine what happens when your curiosity lets you peek behind it. That's what I want you to see, to feel, and to carry with you as we explore the universe together.
Nothing in the universe can go faster than light. Not your fastest rocket, not the most advanced particle in a lab, not even your imagination. Yet, somehow, Richard Feynman, figured out why in a way nobody else could. I didn't do it by memorizing textbooks or following the rules. I did it by asking questions nobody else dared to ask. And that's what makes physics magical.
I suppose you could call me a bit of a troublemaker. As a kid in Far Rockaway, I didn't just take things apart, I played with them. Radios, clocks, even my father's office tools. I wanted to see how the world worked piece by piece. That same playful curiosity followed me all the way to the Manhattan Project and beyond, where I learned not just physics, but how to think. And yes, it earned me a Nobel Prize for Quantum Electrodynamics, or QED, which is my way of saying I figured out how light and matter interact in ways that seem almost impossible. Light itself is extraordinary. A photon moves at 299,792 kilometers per second. Nothing else comes close. That speed is a cosmic limit, a wall that defines the universe. Imagine racing toward it. No matter how hard you try, it's always just out of reach. That's not frustration, it's wonder. What does it mean that nothing can go faster than light? Time stretches, space warps, and suddenly our everyday intuition collapses. The universe isn't a playground for humans, it's a playground for probabilities, waves, and particles. And that's where my diagrams come in. Feynman diagrams, as people now call them, are tiny sketches that reveal the behavior of the universe. A particle splits, merges, bounces, interacts with light, and all of it is captured in a simple drawing. To many, it looks like doodles on a napkin. To me, it's a window into reality. Every arrow, every line, every loop tells a story. How photons dance with electrons, how particles explore every path, how the tiniest elements of the cosmos follow hidden rules. With these sketches, you can calculate the unthinkable. You can see patterns in chaos, order in randomness. That's the aha moment that keeps physicists awake at night. And it's the same magic I want you to feel. Curiosity was my compass. I never accepted the world as given. I asked questions constantly, whether it's about light, particles, or why a safe could be opened with the right combination of logic and patience. That's the lesson I want you to take away. You don't need a lab, a Nobel Prize, or decades of training to explore the universe. One question, one experiment, one thought at a time. You can start anywhere. Ask what fascinates you. Test what seems impossible. Play, wonder. Let your curiosity lead. So here's my challenge to you. What's the most mind-blowing question you've ever asked? What impossible puzzle makes you stop and stare at the stars? Because that spark, that relentless curiosity, is exactly how you peek behind the cosmic wall of light, just like I did. And trust me, once you start seeing the universe this way, nothing will ever look ordinary again. So there you have it. Richard Feynman showed us that physics isn't just about equations on a blackboard. It's about curiosity, wonder, and asking the simplest questions. From quantum mechanics to the cosmic speed limit, he taught us to see the universe in a whole new way. If you enjoyed exploring Feynman's discoveries and mind-bending ideas, make sure to like this video, comment below with your favorite Feynman moment, and subscribe to Feynman Flux for more science inspiration. Don't stop here. Click on another video and keep diving into the fascinating world of physics, curiosity, and quantum mechanics. Let's keep exploring together.